In this nutshell, I look at the ATmega 2560 analog comparator. I show how the internal op-amp is used as a comparator. I show the internal circuits. I show how you can configure the registers for the analog comparator, and I give coding examples. And remember, if you find this video useful, please like and subscribe. The analog comparator uses an op-amp to compare two voltages. Normally we compare an input voltage with a reference voltage. The comparator has two inputs, V plus and V minus, and one output, V out. When V plus is greater than V minus, V out will be 1. When V plus is less than V minus, V out will be 0. So the comparator is used for analog inputs without the need for an ADC. This gives several advantages, including a faster response time, it uses less power, and we don't need to convert the analog signal into a digital word. Common applications of the comparator are threshold detection. We detect when an analog voltage crosses a reference level. For instance, we could trigger a low fuel warning light in a car. Zero crossing detection, that's used in AC power control, or PWM or waveform synchronization, used in power electronics. We can look at the internal circuits of the comparator. The op-amp is shown here, where V plus can be switched between the external pin, AIN0, or a reference voltage called the band gap reference. V minus can be switched between an external pin, AIN1, or an input from the multiplexer. The output will appear on AC0. The interrupts can be used, and they can be selected for a rising, falling, or toggling output on the comparator. And finally, we can use the comparator to trigger an input capture on timer 1. The analog comparator control and status register is used to configure and monitor the analog comparator. The first bit, bit 7, is the power for the comparator, shown here. When it's cleared, the comparator is on. When set, the comparator is off. Bit 6 is used to select what goes into the V plus input. When it's cleared, the external pin, AIN0, is connected. When set, the band gap reference voltage is input. Bit 5 is the output of the analog comparator. Bit 4 is the interrupt flag. It's set when an interrupt has occurred and is cleared by either exiting the interrupt service routine or by writing a 1 to the bit. The interrupts can be set with bit 3, cleared interrupts are disabled, set interrupts are enabled. The bit 2, ACIC, is the analog comparator input capture enable. When set, the comparator will trigger an input capture on timer 1. And finally, bits 1 to 0 are the interrupt modes, and will determine what will cause the interrupt. 0, 0, if the comparator output toggles, an interrupt will occur. 1, 0, if the comparator output falls, an interrupt will occur. 1, 1, if the comparator output rises, an interrupt will occur. So bit 6 of the ADC control and status register is used to control the V minus input. When it's cleared, then the external pin, AIN1 will be input to the comparator. When set, the output of the ADC multiplexer will be input into the comparator. And note that the ADC must be powered off for that selection. And finally, we had the digital input disable registers. This is used to save power if you're not using the comparator. The program below shows a code that will turn on a LED when the voltage, controlled by port 1, is greater than the band gap reference voltage, which is 1.1 volts. So firstly, let's look at the configuration of ADCSRB. We can see that bit 6 is set to a 1 here, and that will switch the V minus input to the multiplexer, which is connected to port 1. We look at ATmux, and ATmux here is setting up a multiplexer which selects port 1 source for V minus. We have the ACSR shown here, so 0 enables the comparator. 1 selects the V plus input to the band gap reference voltage. And then finally, when we look at the port 1 greater than V reference, we are looking at the AC0 bit 5 register. Now note, this could be replaced with 5, but the Microchip Studio actually defines AC0 as 5. So you can use either AC0 here or 5 for this bit testing. And I have inverted it because the VREV is on the V plus, the pot is on V minus, so when the pot is greater than VREV, the output will be low. So I just invert it for my logic. I have written the code into Microchip Studio and downloaded it to the Mega Pro board. We can see that we're using PC0 LED to indicate the state of the comparator. We can see the system running here. This is port 1, and when I increase port 1, we'll see that the PC0 here is set when the voltage is greater than the reference and is clear when it's less than the reference. I will show you the same code again with the display running so we can see that more clearly. So in this example, I am using both the ADC to display the value of port 1 as well as the original code used in the analog comparator. So I'm actually switching between the ADC and the analog comparator here, and I can output port 1 using my display. So if I download that into Microcontroller and have it running, and we come out here, we can see the value of port 1 is shown there, and if I adjust the pot, we can see it going down, and as we increase the value of that pot, once it gets above 1.1, the LED comes on, and then if we drop it down below 1.1, the LED goes off. So we can see the comparator working with the port 1 input. I have rewritten the same problem using a state diagram. We have two states, LED on, LED off. When port 1 is greater than VREV, LED goes on. When port 1 is less than VREV, the LED goes off. We can see that shown here. Port 1 greater than VREV is looking at the AC0 bit 5. same as pot 1 less, LED on, and then we have two state variables, LED off and LED on. We look at our state machine here, the LED is off. If the pot is greater than VREF, state goes to LED on. In state LED on, the LED is on. If pot 1 is less than VREF, the state goes to off. And we can see the same configuration here. Bit 6 is used to select V- to the ADC multiplexer. The ADC multiplexer, we select port 1, and then finally we clear the bit to enable the analog comparator. I have written the state machine into Microchip Studio and downloaded it to the Mega Pro board. We can see that running. It's pot 1 here. When I increase pot 1, when it gets above VREF, PC0 comes on, and then if I drop it down below VREF, PC0 goes off. Now I will once again use the display to show you the value of pot 1. Once again, to make that more clearer, I am displaying pot 1, the value of pot 1 on the display. We can see here I enable the ADC, read pot 1 and display it, and then I turn off the ADC, enable the analog comparator, and basically perform the same code we had before. You can download that to the microcontroller, Mega Pro board, and then we can see that operating. You can see the value of pot 1 here, and as I increase pot 1 and we get up to above 1.1 volts, port C comes on, and then when we drop below that, port C goes off. So we can see that in operation.